In this video, what we're going to do is we're going to do a type 2 signal. A type 2 signal is symmetrical, but it doesn't have a central element. So in other words, you could say that it's a type 1 signal with no central element, and so we call these type 2 signals. We're going to start by applying our discrete time Fourier transform formula, which I'll write here, n minus infinity plus infinity xn e to the minus j w n. Recall that for type 1, the discrete time Fourier transform would give an answer of the form, it would be exponential, and it would be e to the minus j w n sub naught, which would be the central element, times some polynomial, which is a function of omega. We're basically going to do the same thing, but we have a different way of getting some central element, or rather to compensate for the fact that there's no central element. So let's start by writing the Fourier transform. It's 9339, so it would be 9 e to the minus j w 22, because we start at 22 and we'll end at 25, plus 3 e to the minus j w 23, plus 3 to the e minus j w 24, plus 9 times e to the minus j w 25. So what you need to do is to take out e to the minus jw n, let's just call it n, and n is going to be equal to, or rather, so that we're consistent with former notation, let's just call it n naught is equal to 1/2 times 23 plus 24, which is just 23.5. Okay, so let's group those exponentials that have the same factors. So you'll get 9 times e to the minus j w 23.5 times. So you're going to get e to the jw 1.5 plus e to the minus jw 1.5 plus 3 e to the minus jw 23.5 times e to the jw 0.5 positive plus e to the minus jw 0.5. Okay, you can work that out just to make sure that it's correct. Yeah, so once we do that, we can simplify using the trig identity e to the ix is equal to cosine of x is equal to e to the ix plus e to the minus ix, or j, whatever, divided by 2. Okay. So what that's going to give us is 9 e to the minus jw 23.5 times cosine of 1.5 omega right, plus 3 e to the minus j w 0.5 times, sorry, sometimes I say w and omega, cosine of 1/2 omega. Okay, so for it to be in the actual exponential form, we can't have anything in front of e to the minus jw n sub naught. So we're going to bring back the factors 9 and 3. So we have e to the minus jw 23.5. It's 2 times cosine. Sorry about that. I did the same mistake before. So 9 times 2 is 18 cosine 1.5 omega plus e to the minus jw 23.5 times 6 cosine 1/2 times omega. And finally, we can simply minus jw 23.5, take out the exponential, and multiply it by the polynomial p of omega, which is going to be 18 cosine 1.5 omega plus 6 cosine of 1/2 omega. And so let's say that we want to get the modulus. Well, that would be the modulus of the exponential, which is equal to 1. So it would be 1 times the modulus of, don't forget that this is p of omega, times the modulus of p omega is equal to modulus of p omega evaluated at some value of omega. Now, the phase is equal to the argument of the exponential, and that would be e minus j omega 23.5. That's anything that's in front of the complex variable, plus, and I forgot this in the video for the type 1 signal, is the argument of pw. Okay, so this will be minus 23.5 omega, and the argument for the polynomial is simply some constant times, sorry, it's not omega, k pi. And that's it. So I'll circle the answer, or highlight the answer rather, which is all of this. The PDF worksheet is in the description as usual. Thanks for watching.